और सेकेंड हाफ में वेबएक्स वाले को थोड़ा अलाउ करेंगे बाहर म्यूट अनम्यूट करके। अभी इसको सेकेंड हाफ में अभी नहीं करेंगे, इधर ही लिख देंगे 70 अटेंडेंस मैंडेटरी। Good afternoon. So today we will discuss electron microscope. So I have discussed little bit about electron microscope, basics of microscope and why we need electron microscope in last lecture. So we'll see mainly two microscope. That is, one is scanning electron microscope and transmission electron microscope. So these two microscope is generally used to see most of the topological features as well as particle size, shape, morphology. Those type of information you can get by electron microscopy. So just to recapture what we studied last class, little bit basic on electron microscopy. So as you know, why we need an electron microscopy? Well, electrons have much shorter wavelength than that of visible light, and this allows electron microscope to produce higher resolution images than standard light microscope. If you go for a light microscope, your image resolution is not that good. And second thing, you can't see smaller object because based on the wavelength, the visible light has bigger, larger wavelength than that of electron. And electron has strongest interaction with the matter of any radiation. So many types of information can be available, and it is high intensity. Electron beams is high intensity, highly energetic, and relatively easy to generate. You can simple by thermonic emission, you can generate electrons, and that electrons can be used as a source for electron microscope. And it can be used in conjugation with other techniques so that you can get better information, or you can get also like you can do thin sectioning, immunolabeling, negative staining, those things, and then you can see your microscopy images. So in a nutshell, so electron microscopy has much more advantage than that of conventional light microscopy. You can see smaller objects. Yeah. So if we go to the basics of electron microscope, so electron microscope, it's all depends on which type of electron you are collecting. So when an electron beam strike, this slide already we have discussed earlier. So when an electron beam strike on a sample, a large number of electron photons are generated. If based on that, which type of electron or photon beam you are using, so you can distinguish the characterization techniques. So like for example, if you go for scanning electron microscope, so that need backscatter electron, which is high energy electrons, or you can use secondary electron, that is low energy electron of 10 to 50 electron volt. And during that interaction of this incident electron beam with that of matter, you can also produce X-rays. So that X-rays can be used for this element analysis. You can use that, as you know, that these X-rays are characteristic to that particular element, whether it is cobalt, nickel, or manganese. So those type of all elemental analysis you can do, and you can also get a quantitative information from this. If the electron beam is getting transmitted through the material, you generate mainly transmitted electron. So that electron will use mainly in electron microscope. So in electron microscope, that this transmitted electron beams are used. Whether during the interaction, if it loses some energy, then it's that is depending upon what the energy it loses. We can find out that that electron energy loss spectroscopy that we will discuss today also. That you can see how the neighboring atoms, oxidation states, those type of information also you can get from transmission electron microscope. So first we will go to that scanning electron microscope. That simply you can see SCL. If you go to the SCL, you see that you can see this is the image of the top one. That is a SCM image. That first SCM image you can see is as big as a big room size. So scanning electron microscope is a type of electron microscope that produces image of the sample by scanning on the surface of the with a focused beam of electron. Like if you have a surface, if you want to analyze this surface, on that surface, that electron that produce that image of this particular surface by, say, you have a raster scanner on the top surface. So that raster scanner scans along the surface and you'll get a image of that particular location which you want to see. So electrons interacts with the atom in the sample, producing various type of signal that contain the information about the particular element or particular surface. So if you see a historical background, that in 1940s, the first SEM was built by German scientist, the Knoll, and later by Jaroski in USA. So they separately, independently developed that SEM microscope as large as a big hall. So it becomes practically reality by Professor Sir Charles Ottaway lab in Cambridge in 1950. So then the concept is now mature. So from 1950 to today, so that the lots have been progressed and we are able to see very good resolution images, very high magnification, as well as good quality images by scanning electron microscope. So the information that you will get from a SEM is mainly first, the four information you can get most mainly. That is, first is topographic image. You can see this is the surface feature of an object, or how it looks, its textures, its relation between these features and the material characteristics. So mainly you will see the surface feature. You can see here it's an SEM image of a barium titanate sample. You can see at 4 micron and 50 micron scale bar. You can see this how this this you can see that features, the surface features looks like. You have a grain size, you can the granular structure that you can able to see in this image. And if you then another thing, that is morphology, you can also get a shape or size of the particle and its relation between these features and material characteristics. How how the shape and size looks like, and how the shape related to that of particular material properties, how size dependent characteristic you can able to see in other technique. So that you can confirmed by seeing the shape dependent or the size dependent properties by seeing the morphology of an image by a scanning electron microscope. You can also see the composition structure, what are the chemical constituent present in the particular compound or particular element, that object that you can see. The elements and compounds that the object is made up of and its relative amount. The relation between composition and material characteristic that you can find out. That is element analysis is possible by using a scanning electron microscope. That you can also get that how these atoms are arranged in the object, and that arrangement, how it gives rise to different properties. You can also get some little bit about crystallographic information. So that you can also get from scanning electron microscopes. So if you see, so broadly in SEM, the important feature that you see, that magnification is quite high. It is 15x to 200. It's quite large, that you can see up to 2 lakhs magnification. And the resolution is quite high, that is about 50 angstrom. The resolution is quite high, and you can see the depth of focus is here is much higher than that of light microscope. So you can see the jet analysis, that by the depth profiling or the fracture surface, that those things you can easily see, and the sample preparation is quite easy here as compared to other technique. Even when compared to TM, the SEM sampling, it's much easy. And for this sample preparation, that you need your specimen has to be, for SEM it has to be conducting, and it has to be, you can see there is almost no preparation. If a powder sample, you can directly, put on like conducting tape, and that you can also use after a silver paste attaching to silver paste, or if you have a non-conducting sample, you can go for a gold coating or a carbon coating that usually necessary, or chromium coating that to see the non-conducting surface. There is necessity of this coating is mainly due to reduce the charging effect. Otherwise, if this coating is not there, and then what will happen? The electron beam will be accumulated on that surface, and you will see a white layer that will produce the highly charging effect. So to nullify that, you need this. You have to go for this gold, carbon, or chromium coating. Here, the wavelength that used generally, if you have 10 kV, a scanning electron microscope, it's wavelength in the order of 0.12 angstrom. For up to 100 kV, it's 0.039 angstrom. So you have that high voltage you are applying, and sample. Here, the sample stage can be tilted, and specimen, size is limited. That sample chamber is not that big. So in that, you can slightly tilt your sample. So you can able to see the cross-sectional view as well as by breaking it, the fracture surface, you can able to see the SEM. You can see here, if you go for an optical microscope, you can see this structure of barium titanate. Optical microscope OM versus SEM, you can see the 2D of OM, you are just able to see the grain boundaries. When you go for a scanning electron microscope, you see from 50 micron in optical microscope scale here to 5 micron, you can see the step structure growth of barium titanate. So all these internal information you can able to get. That magnification is quite high, that 500 kilo X here, and field of depth is 30 mm, whereas in optical is 0.5 mm, and resolution is also quite good. So you can see the bottom image, that is a radiolarian, that is the image of an object that you can see here in optical microscope how hazy it looks like. You can see in the right one, you can see the what is the all that shape and individual internal structure you can able to see, and each spikes you can able to identify here in case of scanning electron microscope. In Norsel, that optical microscope, you have a small depth of field and low resolution. But you go for a SCM, you have a large depth of field and high resolution structure you can able to see in case of an optical microscope. So the image that produced in this is high resolution in scanning electron microscope, that you can see that here mainly you have a object here. On that object, on top of the object, there is a collector, and then that collector, then there is an amplifier, and then finally it goes to the image that finally produced. So mainly, basically, you have a collector here. The raster scan is here on the surface. It raster that will collect the data. You can say the simply pixel by pixel. Here you can see that the signal produced as a beam spot is placed at each position in turns, that is collected and used for control, used to control the brightness of the display beam. So you can see in this image that pixel by pixel scanning and then reconstruction of image with 1 pixel at a time. You can see this mosaic structure, like this small shapes, small square shapes. You can see here like that your scanning electron microscope do the whole picture. Each pixel by pixel scanning. So each of it the scan, and finally you have to reconstitute that image with 1 pixel, try to get a 3D structure. So if you see here in a scanning electron microscope, first thing you need a specimen that is here as the sample, and then to see the structure, you need backscatter second electrons. So that can produce from electron source. You have electron source here, and the electron source either by thermo emission or field emission, either using field emission or thermo emission, you can create that, generate that electron. So that electron pass through anode and condenser lens, aperture, and then scanning coils. Here you have a scanning coil, a raster scanning coil, and then it has to be produce an image on the image on the sample on the film or the photographic, or you can see in the screen that particular image. So here the high energy, mainly the two types of electron I told, as I told, the backscatter electron and secondary electron. Backscatter electron is mainly high energy that is used for compositional contrast property study. By low resolution, the secondary electron you can use for topographic contrast. And for the composition, that using electron energy, that energy dispersive spectroscopy, by using fluorescent X-ray, you can able to get that dash structure. So brightness of the region in image increases as the atomic number increases. Like for example, if a jet, the atomic number Z will increase. So what you will see, the brightness of the image will also increase. So if a less penetration gives more backscatter electron, like you have a higher penetration, then probability of you generate second electron, but if you have less penetration, you will get mostly backscatter electron, and that electron can be used for this compositional analysis with the backscatter electron. So you can see the electron is generated from a electron source. That electron beam source is there. You can see you have you can use thermonic emission that only rely on the heat to generate electrons. Like you can see the tungsten filament, and it's on the top surface anode, but due to the potential difference, large potential difference, what will happen? So you will generate electron from the tungsten element, and if you have a field emission source, that is the Fiji source, use strong electrostatic field to induce electron emission. But in thermonic emission, generally we use tungsten, lab-6, or cerium hexaboride, or tungsten tip, those type of tips. You can see this is circular type, this is a needle shape, this is a little bit broad, and then it's sharpened needle shape. So you'll able to see that by using this, electron beam, that is useful for generating the characteristic images. So the SEM requires high current density, that is as well as small electron spot as possible to get better images. So the thermonic emission, you can also use that electronic gun that can be used here, so that in filament heated to give thermonic emission is mostly tungsten. Lab-6 you can see this is tungsten one. This is a lab-6 one, how sharp is this tip in case of lab-6. So filaments used to kept at a negative potential to the ground, and one let produce small negative potential. The small negative potential will be generated here. Here the small negative potential generated is here. So that, and the types of tungsten needle is made up of very sharp, like you have a sharp needles or a tips. So that also depends on the electron, that the emission property also depend upon how sharp is your needle. You can see here you have a high anode here, an electron beam is here. You can see from the filament, because of the high tension, high voltage once you apply, or due to high heating, because of heating the electron will lose here, and then electron will pass through the anode here to target to the particular films, or you can see the image on the screen. So it's similar like FEG electron guns in FEG, it's like this thermonic like tungsten or lab-6. The electronic gun are also used. Like in FEG field emission gun, a strong electric field is used to extract electrons. Here you can see here there is a 2 anode system. This is the initial setup. Then there is from here the hydrogen will be produced. There is a extraction anode, then there is an acceleration anode. The first anode, that is extraction anode, the second anode is that V2, that is called that is electrostatic lens, that is mainly acceleration mode here. So you can see once electron generated here, it gets extracted, it has to high potential to remove that electron from the source. Once it comes inside, you have to go to the activation anode, that is it will the acceleration anode, so that will accelerate that electron velocity, electron energy, and you will be able to get high energy electron you can bombard on the surface. So you can see here you have tungsten. You can see that how this resolution D is there, and you can how the energy is 1.5 to 3, and how the brightness you can see in the tungsten 10 to the power 9, whereas to the lab 6 and again 10 to the power 9, 5 But if you go for the cold FPG, you have a 10 to the power 13 that high thermonic emission, that brightness you can able to get. Here you can see the sharp tips of that some electronic gun. And then for the generating electron gun, all these things you will get, you have a applied voltage as well as a vacuum is necessary, since these are high, you have to use a high energy system, so you have to use high vacuum also. So if you have applied voltage, like the resolution increases, as well as your lambda will decrease, your resolution will increase, and penetration capacity also increase. Specimen charges maybe increases in case of insulator. If applied voltage is increasing, and image contrast also go bad because of the electron applied based on the electron applied voltage. And then you have to do all these experiment in a vacuum that is chemically corrosive, chemically chemically non-corrosive, and thermal stability is necessary for a well-functioning filament at a particular gun pressure. So FPG is generally high 10 to the power minus 10 torr pressure you need, whereas LAV6 is less than 10 to the minus 6 torr, is necessary. The signal of the electron must have traveled from sample to detector. Once signal is produced in the electron, that has to travel to the detector, to measure it, and then vacuum requires is dependent on the type of detector you are using. Whether you have backscatter or secondary electron, that vacuum accordingly you have to decide. So if you see the optics of that microscope, scanning microscope, like conventional microscope, you have magnetic lenses. Here it is magnetic lenses. So because of the magnetic lenses, there will be field that start schematic cross section of a magnetic lens and light optical analogous to with a convex glass lens. Copper wire is coiled inside in iron cylinder, and rotationally you get that symmetric or inhomogeneous magnetic field. So you can see here these are the magnetic lenses. So that act is equivalent to that normal lens. So because the magnetic field here, this will be deviate from the path, and you're able to see the particular image in case of SEM. So if you go for the conventional SEM, you can see this is the light source, object is here, but you are seeing your objective is larger and it's oppositely faced. But when you have a scanning electron microscope, through this small hole, you can able to see that object, and then you can able to see the image that is in the display image in the same direction, and you will get bigger size image here. Instead of registering image in eye or recognizing it one film, we can scan it and transfer to TV display in case of conventional microscope. And the scanning microscope, the resolution is determined by probe diameter. But the probe diameter that electron is emitting from there, that decides mainly the resolution. And magnification is not related to the M, is determined by the ratio of the display of area to the scan area, the scan area M, and this is the that magnification can be related to the both the M as well as ratio that is to the scanning microscope. So for this scanning electron microscope, you need a detector. So that detector can be either a backscatter electron detector or a secondary electron detector. Here in case of backscattered, then you use solid state detector. So electron of energy up to 30 to 50 kV, much higher energy electrons are produced here, and then for the capability of detecting that an annular around the incident beam to repel secondary electron beam with biased mass. So detector sites above in the sample below the object lens. So detector mainly lies in the above the sample, but the below the objective lens, we strike it to detect. So images are more sensitive to chemical composition. That electron yield depends on the atom number. Based on that, the images are sensitive to chemical composition, you can able to identify. So if you have a secondary electron detector, that is mostly PMD detector or scintillator detector, here bias mass is 100 volt to 300 volt needed in front of detector to attract the low energy electrons. So whatever the energy, with the low energy to attract that electron, you need front detector, you need a bias mass is necessary. So then if you see the detector, if you see the magnification in SEM, the magnification is accompanied by the scanning a progressively smaller portion of the specimen and the displaying the image in CRT. The total magnification, you can see M equal to L CRT minus L specimen. That's the total magnification is the square ratio area of CRT divided by the scan here. You can see change in magnification at working distance. You can see this is the image and this is no image rotation. If you have a change in magnification at constant working distance, if working distance is constant, the sample surface to lens, this distance is constant, and you can changing the magnification, you can able to get different type of picture here. And if working the distance in constant magnification, like image rotating, like changing working distance at a constant magnification, if you see that this type of picture you are able to see. So magnification will be LCRT by L specimen here. So magnification is connected by the change in the strength of the scanning coil. So if your scanning coil strength, the change goes bad, then you will be able to see bad images. So if you go to that, yeah, you can see here, if you go for the scanning, so how the zooming image on CRT, you are able to see. So based on that, the magnification you can define LCRT by L specimen. So then when electrons are highly energetic, your depth analysis, depth of field, that DOF is the distance along the optical axis, either side of the focus point that remains in an acceptable focus. This is the highest over the sum which sample can be clearly focused. So using this depth profile analysis, you can able to focus the image. The SEM has a large depth of profile which provides the images that appears 3D in nature. So depth of field here, you can see the image, the top image and the bottom image, the SEM image of the pollen. So you can top one is taken as a 8 mm working distance, so the bottom one is below 37 mm working distance and 100 micron aperture. You can see how the image quality it changes between this. And this depth of field is mainly longer for longer working distance, smaller object aperture, long working distance, smaller object, lower magnification. In that case, you can see this type of profiling. So you can see, you can also get the topographic image or morphological image of the sample that you can see here. If you go for SEM imaging, and SEM image focused at high magnification will still heavy focus at low magnification. You can fix here the first low 110x low magnification, so you are able to see nothing here. So charging effect has to be nullified by coating with carbon or gold before you to see the SEM image. So but in 10x, you are able to see this type of image, and then you go to 110x, you can instead of here seeing the whole ring, so you go to the first layer of the ring, and you can see how this 10x magnification, the image is differing from that earlier one. And you go to the 200x, where each grain boundary is clearly shown that information, and it's more clarity you can get it. 400x, you can see there are few particles and how they are conjugated, how they are attached to each other. You can see. And then further magnification 4K, you got internal structure that this type of internal structure you can able to see here, those type of information. And then you have a board here, so that information more broadly. So 16x you'll able to see this one, whereas 45x you will be able to see the much larger and sharper image for SEM analysis. So if you go for SEM imaging, that we are using two type of electron. One is scanning second electron, and there is backscatter electron. And then we are also dealing with X-rays. You can see here the cracked surface of an insect hair. It's an insect hair. You can see this is the second electron, this is the backscatter electron. You can decide which type of electron image better in terms of sensitivity. Okay. But in case we can see the right image, a bacteria image, when you have a mixture of backscatter secondary, you can see better quality image, and only backscatter you can see here. So topographic imaging is possible by using scanning electron microscope, and the backscatter electron is high energy, and it gives mainly compositional contrast, things like brightness of the region of an image increases with as an atomic number increases. Like Z value increases, the brightness of the image will also increase. The second electron, which is produced from inside the material, that is of low energy, we mainly use topographic contrast. And high resolution image can be possible. And for the fluorescent X-ray that is produced, you can able to see the composition by using EDS analysis. You can see here you have a scanning electron microscope that is the EDS energy dispersive spectroscopy. You can see in this spectra that you can see carbon, K alpha, oxygen, iron, silica, phosphorus, magnesium, all these elements that you have taken during your in the sample that analysis can be possible. So here, during the process of generation of secondary electron, a vacancy is created in the electronic state. And if you have an atom here and that electron beam falls here, so this will be knockout and you will get a vacant, there will be no, you will get a vacant site here. And then what will happen? The outer cell electron on the top, that electron fills the inner cell. This will be filled and vacancy producing an X-ray photon. So you generate an X-ray that will generate because of this, decrease in fluorescence intensity. So each element has a fingerprint X-ray signal. So you can use by K alpha or K alpha analysis when able to find out the elements. So energy dispersive spectroscopy based on the mainly energy of the X-ray, depending upon the energy of that particular X-ray, so that each elements can be identified by using scanning the exact specialty of scanning electron microscopy. And it's determined the amount of element level in present is 0.1 atom percent. So at very, very low concentration, you are able to get these information by measuring X-rays line intensity. Then full point line, area scans, analysis, electron analysis, so those can be. So we'll discuss that. So you can see here, if I have manganese dub zinc sample, then you can see the manganese K alpha, the cobalt dub zinc and cobalt K alpha, and how equally mostly they are distributed on the surface. So those information you can able to get from the analysis. So then, so far that SEM, scanning electron microscope, uses high this vacuum is necessary. But biological samples or soft sample, you have to go for another technique that is called environmental scanning electron microscope. So that is used to image challenging sample like insulating sample, vacuum sensitive sample, irradiation sensitive sample, and then that you need this type of different insulating sample. Then you need SEM scanning, that environmental SEM is necessary. But normal SEM, what will happen? So these biological sample, a thin organic film, they may sometimes burn out because of the high voltage. So you have a high vacuum needed. But in case of environmental SEM, that is possible even at low vacuums. So it's also huge image chemical and physical process in situ. So during in situ, like mechanical stress testing, oxidation of metal, hydration, dehydration, watching the paint dry, for example, you can able to see that how challenging to teach SEM electron microscope, scanning electron microscope, and how ESEM is overcome that by using sample at low vacuum, and you have a nitrogen environment there, and at low vacuum can operate that SEM can preserve the biological structure here. Traditional SEM chamber pressure is -6 torr, the ESEM is 0.08 to 30 torr. So here different gas can be used inside that, and then you can able to see the scanning electron microscope. So basically, the scanning electron microscope mainly uses to see the surface morphology, topography, as well as composition analysis, and little bit of crystallographic analysis. That part I'm not discussing much. So that like proposed IMDb FIB, that is conjugated with the attached together with the SEM, then you can do all the crystallographic orientation, crystallographic analysis by using SEM facility. And you have a biological sample that for that you can use a environmental SEM that is operated low vacuum, and then some of the structure can be preserved, and using nitrogen environment you can able to see that how the images are looking. So, and that what are the K alpha, that X-ray fluorescence signal is producing here, the K or L. So that X-ray signals you can use to analyze the chemical composition or the elemental features is present, and then you can see if you have a you can see how this manganese is docked inside ZNO. You can see the copper K alpha, like manganese K alpha spectral map. You can see these light dots. So that indicates the position of the manganese ion. It is almost uniformly distributed, and here you have a sensitivity up to about 0.1 atom percent able to measure by using this type of scanning electron microscope. So now we'll discuss about transmission electron microscope. So before that, we'll take a 3-minute break here. Then we'll go for transmission electron microscope. So now we'll go to this discussion about transmission electron microscope. So like before going that, so I'll just inform you that those who have taken this this course has a credit course, so they have to be, 75 attendance is compulsory for, to appear the exam. Otherwise, they will not be allowed to complete this course, and the proper credit will not be given. So you have to minimum 75% attendance has to be given, and each student has to mention their, registration number, both, that YouTube as well as your WebEx. So they have to give their registration number, so that, that we can mark it, and accordingly that 75% attendance will be considered at the later stage. So now we'll discuss transmission electron microscope. So it's only difference that from the scanning electron microscope, there it used backscatter electron or second electron, and the surface they will raster scale, so that raster scale scan the surface. But here instead your electron is transmitted to the material, and then you'll get an image at the bottom, or you have a detector that will be able to detect and you'll be able to get that image here. So if you see the historical background of the TM, so you can see the TM is Ernst Ruska and Knoll. So they first, started that use my combinedly first electron microscope in 1931. That magnification about only 400x was produced by these two scientists. And later on, Ernst Ruska awarded Nobel Prize in 1986 for the discovery. And Simon then developed the first commercial TM in 1939 after a long gap, and all modern electron microscopes are based on Ruska prototypes. And now the resolution from 400x to 2 million times that can be achieved in today's transmission electron microscope. Here, the TM is a unique tool to characterize crystal structure. So you can able to see the crystal structure by using TM. There is microstructure information you can able to get from the TM. And these electron microscope are operated like transmission electron microscope operate at very high voltage, like 1000 kV or even 200 kV or 300 kV transmission microscopes are now available. You can see here, if a UV light you are using 365 nanometer, your wavelength is about 365 nanometer, and resolution is only half of that, about 159 nanometer. But when you go for an 100 kV TM, your lambda is 0.0035 nanometer, and your resolution is 0.24 nanometer. You can see how enhancement is possible by using this transmission electron microscope, and you can see that sufficiently smaller image, like you can see, are able to see the atoms because of the wavelength is quite low, and lens information there is one share some up, though there are some aberration state that are available here, possibilities here like spherical aberration, chromatic aberration that limited the resolution. But nowadays these type of many corrections are available with microscopy TM, you can able to see better quality images. So here you can see mainly the incident high kV electron beam. So that electron beam, fall on the sample surface, and the sample is here, it's very thin here. It should be less than 100 nanometer. That but electron to transmit, you generally use transmit grid, that copper or molybdenum grid on which you are depositing by powder samples. Or if you want to metallic sample, you have to prepare very thin slice, like less than 100 nanometer. So electron wave will transmit through that, and you will get a direct beam as well as elastically a scattered electron beam as well as inelastic scattered electron beam. And then there's some X-rays can also produce in case of TM, and that X-ray will be used for element analysis by using EDAX facility of TM. So here, the direct as well as elastically scattered beam that mainly used to produce images, which due to mainly contrast difference at the mass and thickness difference, like you have a specific mass is there, so electron transmission will be less there in comparison to the where is absent. So based on that, you will get a image, and you can also get diffraction pattern from where you can get information about the crystal structures. And then X-ray that's produced that can be mapped containing information about element analysis. And inelastic scattered, where the electron that is inelastic scattered means during this transmission process, it loses some energy. That inelastic scattering electron can be used for electron energy loss spectroscopy, yields analysis, and that containing elemental or chemical information will also get from yield spectra. You can see that this is a schematic of the right side, the schematic diagram of an EM, and left side is a microscope image. You can see here is quite complicated, and this system, and the top surface you have an electron gun like SEM, you have electron gun the top surface, then inside there are many lenses are there, condenser aperture, objective aperture, and then you have a specimen here, and finally it transmits the fluorescent screen here where you will able to see the image. And at this position you have a detector, that redox detector, where you see the elemental mapping. And here that if you see that many lenses that are arranged here, so that many lenses is just to focus the electron beam, and you have a condenser lens, an objective lens, again for these magnetic lenses bend the electron beam, and then it finally fall on the sample surface, and again goes through the different objective lenses or projector lenses to get that image at the bottom using either fluorescent skin or using a camera or 2D detectors. You'll able to see that a particular image of it. So here there are two modes are possible in case of TM. The one is imaging mode and another is diffraction mode. The only difference between two modes be the strength of the intermediate lens. So depending upon the lenses you are putting the aperture lenses, so you can able to get that either a diffraction mode or imaging mode. You can see that the top surface in both cases, imaging or diffraction, you have electron ground on the top surface, then it goes to the condenser lens, it falls on a specimen, and then you have a electron beam, the transmitted electron beam here, the direct beam as a diffracted beam that I will discuss. It come and fall on the objective aperture, go to objective aperture, and then you have here you have intermediate lenses is here. So in the intermediate lenses, you can see there is a image on the back image plane of the objective lens here. So the position you can see here in imaging mode at this top, and here it is at the bottom. You can see here is the center of that where the point all the diffracted and direct beam are meeting. So there is the objective lenses here, image plane, the objective lens is kept here, and depending upon this strength, you will able to see here diffraction pattern. You can get only spot, but here you can see a large image is possible in case of imaging mode. So mainly difference is that intermediate lenses use that strength changes between two regions. So because of the strength change, you'll able to see either imaging or diffraction mode. You can see here that electron diffraction pattern. If you see that the incident beam, you have a top incident beam here is coming and it should transmit to this direct beam if without diffracted. But so because of the diffraction, what is happening that the image is transmitted to in this direction. So you have a small angle here, diffraction angle is here, 2 theta is here. And then because of this, so what you will see that whenever that Bragg's law will satisfy, you will able to see particular diffraction pattern. You can see. So there is a two lattice plane here, is a red plane and is a green plane here, corresponding to the center beam is here, dark green here, and the corresponding to the lattice plane of 1, you are seeing 2 spot, red spot. Based on the lattice plane 2, you are getting 2 green spot. So best like that, you will get different spots on the screen, and then this you can analyze those spots to different planes. You will able to get that diffraction pattern, which will confirm that you are getting what you are getting with the X-ray diffraction spectra, and you can correlate with electron diffraction spectra. You can the pattern you can able to see that whether the crystal has been formed with a single crystal or a polycrystalline structures. Those information you can able to get. This is a silicon 11011 orientation. You can see this is the center 000 spot, and from there 200 200 bar. So all these dots can be identified. That we'll discuss. And if you have a see the electron diffraction pattern of a this is mainly in case of dot, you will get a highly single crystal structure. But if you have a polycrystalline structure, like different planes are there, you can see red, yellow, this blue, green, all different planes are there, then what will happen? So you will get a ring type of structure, because for each from each grains here, each color pattern in this grains will have a particular, like for example here you will get for example 200 plane of a black one, then it's a red one, then that of blue one, green one, or yellow one. So they all will be come here and it will join to each other and you get a ring pattern. And similarly for the another plane you will get another ring pattern. So in a polycrystalline structure like here I have shown here on right side, even this is even 2001111 2203. So all the dots are conjoint each other, and you are able to see some ring structure. This is mainly a feature of a polycrystalline structures. So if you see the electron diffraction pattern, you can identify whether a matter is amorphous or polycrystalline or single crystal. You can see here, if an amorphous, but there is no long-range ordering. Because of that, what you are getting the diffuse ring. These rings are quite diffuse. You will get a highly diffuse ring. But you have a single crystal like structure here in this bottom one single crystal, only one directional plane is here, and then what you are getting only dot. So single crystal most order structure, an electron beam passing through the single crystal will produce a pattern of spot. So you'll able to get only spots you will get. And crystal structure, lattice parameter, and orientation can be determined from these points. And if a polycrystalline structure here, you can see that many grains are there, they're oriented in different direction, their orientation. So because of that, what you will see is made up of many tiny crystals. So, each crystal can be these are all single crystal grains in polycrystalline material have random orientation. Like many, here is one single crystal, so you can say many composed of many single crystal is the polycrystalline material. So here the diffraction pattern looks like a superposition of all dots that I told, and you get a ring type of structure. And this ring is resulting a concentric ring around this the center beam spot you will see, and crystal structure, lattice parameter, all these information you can able to get in this. So so here like the only when the Bragg's law satisfied, then only that electron diffraction pattern will occur, and phase identification and defect characterization can also be possible by using electron microscope. You can see here like similarly UL sphere, like all dots what you are seeing here, then if a incident beam is coming here from this is the center, all the spot lies on this sphere, that UL sphere, then you will able to see that diffraction spot you will able to see. That you can see that's normal sine theta, you write in the lambda equal to 2d sine theta, that you write that normally that in Bragg's equation here. So this is 1 by lambda, it's 2 theta, then from G you can calculate the sine theta from this equation, or you can simply write lambda equal to 2d sine theta as Bragg's law. But for a small angle, as I told here, that this here you can see here the angle is very small. In case of transmission electron microscope, the diffracted beam angle is very low angle. What will happen? So lambda equal to 2d sine theta. So this sine theta will be almost theta equivalent to theta. What will can lambda equal to 2d theta. So here, and then that by geometry of diffraction, so need to right angle here the triangle. Just 1 minute. So if you see this equation, that this right side here, so this is a specimen here. On the specimen, that wherever that UL sphere here, see that this is the incident beam, the transmitted beam which is passing through here, then it's a diffracted beam here. This is 2 theta, that angle, and this center to this distance is r, and this length of this is l. If you have, then what will happen? The r by l, that is r by l will be your 2 theta. That is this from 2 theta. Then from these two equation, So you got RD equal to lambda L. So R equal to the radius of the ring that you are getting the diffraction pattern. This is the diffraction pattern. This is the ring pattern that you are getting. On that ring pattern, the center to this distance is R. And this is R, and this is the camera length. If you know L, then what you will find. So this R is you can measure from the image, and L you can get from the electron microscope, and lambda is fixed that you are what are the energy you are using, whether it's 100 keV or 200 keV, and D, that D spacing can able to find out very easily from this electron diffraction pattern. You can able to see that whether it's 100, that whatever the value you are getting in the 0.2 or 0.25 or 0.28 or D spacing you are getting, so corresponding which plane is there, so you can match it, and then you can able to get that different plane. You can identify each of those planes you can get here. That. So you see that you can see here, this is a ring pattern that is a electron diffraction pattern, affinity of a structure. Here the radius of each ring is characteristic of interplanar spacing. So each ring radius from here to here. So this radius distance to that will be each ring will be give you different characteristic of that particular plane. So it measure the diameter of the ring. Since in this image you can use the images software, and from the images software what you can use. So here the center is getting difficult to focus find out the center here. So better to measure the diameter by seeing to the oppositely lighted spots. Like here is one spot, here red spot, here the white spot here, and the corresponding opposite spot is somewhere here. Then you can identify that line you can draw, or this to this line you can draw, and then divide by 2 you can get the radius length of that radius you can find out, and then for the camera length L you can able to find out the index that structure. But nowadays the earlier images you are used to get from the photographic film, we get that this unit is about nanometer scale, but now the modern PM is giving nanometer inverse, 1 nanometer scale. In that case, this equation is taken into consideration by the instrument itself, that camera length and lambda, and what you have to only do, you need not to do all those things. So simply you measure the diameter of this, and then you divide by 2 to get the radius. Once you get radius, since it's a reciprocal imager 1 by nanometer scale, you simply get from R, you try to find out 1 by R, that whatever the 1 by R value, that will be the D spacing of the first plane, and then you can go for the second plane and third plane, and each plane on 1 by R1 will be D1, 1 by R2 will be D2. So like this, all the ring structure you can identify easily. Like I have given here, you have a simple cubic, so you can use this type of formula, that N by S square from relation to the interplanar spacing, and then if FCC, BCC, all those you can able to get Miller indices by using this equation that I discussed already in the XRD pattern analysis. So if you have a single crystal structure, in that case you can't be able to use this lambda equation, L lambda RD. For that, what you have to do, first measure the distance of the diffracted spot from the center point. If it is the center point, from the center point, what you do from here, that you measure the distance correspond to the D spacing of the reflecting plane. So this and this you can measure, like here the distance corresponds to the D spacing of the reflecting plane, and hence related to the camera length L. And once you measure these two distance, and this will be in HKL of this will be G1 plus G2. Once you find the HKL value of this or this, and you can able to get easily the third one, like for 0, 0, 0, if this plane is 1 bar 1 0, this is 0 2 0, then this will be addition of this 1 bar 2 plus 1 3 0, this plane. So the simply you can find out that by summation here, the angle between the lines drawn from the central spot to the diffracted spot, if H1 K1 L1 and H2 K2 L2 are the angle between the planes here, you can single. If you know the indices of closed set of diffraction spot, it is easy to identify because of the vector addition. So every diffraction spot can be reached by a combination of these two vectors. By combination of the vector addition, you're able to identify all these, like here, from here to here, you can able to identify this. From then again, if you keep this at the center, you can, although you can calculate. So you can, all spot pattern can be identified by measuring the distance of the diffracted spots from the central spot. So that, and you can easily find out the structure. Like from the, if amorphous structure, from the amorphous structure, it's very difficult to identify those, information. But nowadays, that in TM, the radial distribution function that you are getting. So this new technique that's called fluctuation microscopy, where it happens, where that from the ring pattern, the intensity from diffraction ring will find out, and then from that intensity, how the intensity of the diffuse ring is changing from one center to outward, and then you will able to get a radial distribution function RDF. If you plot like angstrom, that radius from this, that fluctuation, what you are getting, that peak, that from this, how the radial distribution function can be recorded and measured, and you can able to get some medium range ordering or second order correlation, those type of some ordering you can able to find out in case of by using this new technique, fluctuation microscopy, that's part of a newer TM microscope. So far what I've discussed is mainly associated with how the TM produce diffraction pattern for different, for amorphous, for polycrystalline and single crystal, as well as how you can identify and each planes in a polycrystalline material or a single crystal spots in a diffuse ring, you can use to get the radial distribution function, and then from there you can get some information about the material, or this you can able to get. So now we'll discuss the imaging part, the second part of that of TM microscope. So the imaging of a specimen is formed selectively, allowing transmitted beam that or a diffracted beam down close to the microscope. Like if you are transmitting allowing a direct beam, or you are diffracted beam. Based on, if you are transmitting a direct beam, then it is called bright field image, and your diffracted beam, it is called dark field image. And the origin of the image contrast is the variation of the intensities of the transmission. Like you have a material here, and this part is thick and this is thin. The transmission here is less intensity. Here transmission is much high intensity transmission. So the origin of the image is the contrast between this high and low contrast. From that contrast difference, you can able to see the image here, and that in the diffraction condition depend on the microstructural features of the electron path. So you'll able to can see here, you have an electron ground here, then condenser system, here is specimen, and from this specimen the electron is beam is coming. This one is going straight. So this is your direct beam, and this is direct beam here. And if you are using this direct beam, and this is the direct beam, then you are getting this image here, image of this image using the direct beam. What will happen? That will call bright field image. In case of allowing the transmitted beam, you will get bright. If you are using diffracted beam, like this beam, you can see after falling here, this beam is diffracted, and then it's coming here, and this is diffracted, and then it's coming here. So if you are using diffracted beam, then you will get dark field images. So based on these two techniques, so you're able to see the final image on the screen. So the different type of imaging that you can do, one is mass thickness construct. Depending on the mass, the Z value that you will able to Z contrast imaging is possible. The contrast appear in the image due to a difference in the inherent scattering of the sample. Like you have a copper, and the core and the cell is something silica, then copper is the high Z and silica is low Z. So you can able to see the mass contrast of the copper and Z. You can able to see the core cell structure. And if you can also use a diffraction contrast, that is a crystalline material diffraction occurs, and that in crystalline material utilizing the objective aperture either in direct or beam or in the diffract beam, you can select the images can be result. So you can use a diffraction contrast image, and you can also get a high resolution image, that is by phase contrast, where both you can use both direct beam as well as diffract beam. Both beam can be used to get a high resolution image that individually we'll discuss each. So first we'll come to bright field image formation. You can see here, this is the optical axis, and then the sample is here, HKL plane AB, the sample here, then incident beam is coming here. So this incident beam is coming directly here. This is direct beam is coming here. So then you have a spot here. You can see this meeting here. This diffracted beam diffracted plane is here, and the transmitted beam is passing through, and you are able to getting an image here. So here you are using the direct beam, and it is falling on the sample, and the direct beam after falling on the sample. So the direct beam is passing through the sample, and you are getting the image. You can see here that is the dark one here, the blue spot, and that the image is you are getting from here. So it's directly on that, on the surface. So diffraction pattern will looks like this. So because of this direct beam we are using, so image formed from the direct beam, so that we will call it a bright field image. And objective aperture is placed. You can see the objective aperture that is there, so that is placed on the back focal plane of the object lens, which allows only the transmitted beam, to pass. You can see here the direct beam which is here, so that beam is passing here, while the indirect beam here you can see diffracted beam, it is falling here, and if it's meeting here, so this diffracted beam is not passing through the microscope to create the image. So that the indirect beam, that the diffract beam is stopped here, and only transmitted, that direct beam is transmitted, beam is passed. So in this case, the mass thickness and diffraction constant contribution to the image, both mass thickness and the diffraction contrast will come, and you will get local contrast on TM image plane is proportional to the number of electron striking or viewing on the screen of detector. So whatever the electron beam transmitting from that particular sample, depending on the mass thickness, it got an issue, got strike on the detector, and depending upon that intensity of the electron beam, the number of electron, you will able to see the image on the screen. So objective aperture in different size can be selected for images of different size. Objective lens aperture can be selected to get different images. So it is the objective aperture is mainly here, that allowing only the direct beam. It's not allowing the diffracted beam here. So in that case you are getting bright field image. But if you go for the dark image, you can see here that image, that objective lenses placed somewhere, then you have a objective aperture here. You can see that aperture, so that direct beam which was coming earlier, so that was passing through this orifice. So now it is stopped by the objective aperture. Only the diffracted beam, so that is here. So the diffracted beam which is falling here, that the 2 theta, the Bragg's law satisfied, then it diffracted, and that beam is transmitting through this objective aperture to get that image, which is called diffracted beam. You can see, so this is the center beam here, so that is getting stopped, and this diffracted beam is using here. So because of the diffracted beam, either you can use multiple or single, that because of the diffracted beam, you will able to get the image that is mainly called dark field image. Here, one or more diffracted beams are allowed. You can see here in this case, that is one diffracted beam is here we are allowing. Here is a 2 diffracted beam, 2 diffracted beam that is allowed to get to the objective aperture, the back focal plane here, to get the image that is called bright dark field image. So in case of bright field image, what you will see earlier case, this is bright field image, your sample will see dark in the screen, but in case of the dark field image, your dark field image, your sample will see bright in the screen. So that is the main difference you will see in case of dark field and bright field image. Mostly dark field image are used for the grain structure identification that we'll discuss. So if you go for dark field image formation, so dark field that you can see, this the direct beam is stopped here, only the diffracted beam, indirect beam that is coming, so that is passing through the objective aperture to create the image. So there is 2 type of dark image. So here the dirty dark field is produced here in this case, that this is the aperture is kept such way the diffracted beam is passing through this aperture, and you are getting the image. So this is diffracted beam is going through, but the center position is getting blocked. So that is called dirty dark field image. But center dark field image is such that your beam, your incident beam here, you can see it is falling perpendicularly. It is perpendicularly falling on the sample surface and then diffracting here from the sample. But in center dark field, you can see your incident beam is aligned in a particular angle that from the center beam, from the central position, it's aligned in a 2 theta angle. So in such a position that the incident beam is aligned, what is happening? You can see that after sample surface, you see that this is the direct beam, it should go like this and that will stop here. But after here, you can see here it's diffracted and it's falling here and directly it's going through the, it looks like a bright field one, like discussed, is going straight and then passing through this image. This is called center dark field image. So image from the two diffracted beam that I am, this is on axis diffracted beam, so off axis. You can see it's off axis because it's going deviating and then you are getting through the aperture. But here the center position is here, the aperture, and by using that the sample is kept in such a way and that the incident beam is coming to the sample at a particular angle, and then after falling it is going as a it's falling the aperture at right angle. But here it is on the sample it's right angle, it is falling on the aperture right angle, and then it's going to the objective lens is right angle of the objective lens, and it's going to objective aperture to see the image. So here that the two type of image that I discussed, so you can use for either one depending upon your interest of analysis, either bright field image or dark field image that you can use. Like as I told, that one is mass thickness contrast, that you can see here, if a mass thickness contrast, so that image is incident beam is coming here, then that this side you can see this is a low Z and this is a high Z. At low Z you can see the transmission is faster and here intensity is high, but here that is mostly it will blocked by the low Z, the high Z one. That because of that you can see the opposite image here, and this side you can getting that contrast accordingly, high contrast. Here you will less intensity profile you will get depending upon it. So contrast is a function of Z, that's mass density, and more the scattering will be observed at high Z material, more scattering, so transmission will be less, and depending upon that people are able to see the image. And similarly, for thickness, if like high thickness material, more the scattering, and higher thickness you will be able to see. And important, if a polymer, amorphous or biological sample, so those type of structure you can able to see using a low electron volt TM. Like here you can see it's Fe3O for SiO2 structure. You can see here this core is this Fe3O4 and cell is silica. The Fe3O4 this core, that Z is low, silicon Z, and it's outside is so outside silicon is low, for a center this Fe iron Z is high. So because of this you can see this contrast different, you can able to see the mass thickness contrast image, you can able to see the core cell structure identification by using transmission electron microscope. Core cell analysis can be possible. And if you go for bright field and dark field, as I told, so you can see this is a bright field image, these two. So here you can see the spots are showing like gray or dark here, but whenever dark field image you can see each grains are here, background is black, but each grains are showing white spot. So this is a white spot that indicates it's a amorphous structure. It is mainly black one, and then amorphous how the grains are present, so that you can see in this type of dark field image. So mainly here how you can see each sphere is made up of many small nanocrystals. So it's structure, you are able to see how these small nanocrystal aggregate to form a big cluster, and how this center dark field image you can use to see whatever the structure you can confirm by using this grain structure through this dark field image. So in addition to that, both dark field and bright field, there is another STEM is possible, that is that the STEM you can do the scanning transmission electron microscope. So like SCM here, there is raster scanner is there, and that raster scanner, a normal TM sample lens goes to lens, and you have a camera, lot of lens, and you go to camera. But here in case STM, you have a raster here, so that raster will what will do, it will scan on the surface, you will get better image contrast, and lower beam damage, so the beam will not damage here the sample surface, and you can see that it's a TM image of a steel sample, and this is an STM image. You can see in the STM how this, whatever the inside feature and all this grain feature, that you can able to see more clearly here in comparison to that of TM, because of the raster scanning on the surface, and simultaneously you can do energy dispersive spectral like the element analysis or yield analysis in case of using this TM also. Here you have a detector, that's high definition detector. You can see high angular dark field detectors. So because of the high angular detector, so you can able to see better quality image in case of STM. In STM, as I told, you can able to see all this EDAS analysis or SCM analysis. You can see this is an STM mapping, that after that STM structure, you can, I have just scan across this particle, and you can see along this how the cobalt and zinc, it's a cobalt of zinc oxide sample. So how cobalt is, the presence of cobalt or that zinc, that you can able to see in this spectral analysis. From K alpha energy, you can identify all these spectral mapping, you can identify that elements. So you can, after you along this line of wave scan, you can see you have a spherical surface on the top, that you will get high, less like if you go like this, you will go inside. So what will happen in the center, that more and more particular that distribution will be on the surface will be less, at the center will be high. So because of that, in the core, what will happen, that you will see a hemispherical shape structure. So that will see whether the dopant agent is uniformly distributed in your structure. From the hemispherical spectral mapping, you can able to see how this cobalt is doping, was uniformly doping throughout the structure. You are randomly substituted. So those information you can able to get by spectral mapping. You can see here, this is the zinc scanning, a red one, zinc K alpha, but iron K alpha is where the Fe is dropped. This is the structure where in zinc oxide on which Fe3O4 particles randomly distributed here inside this. You can see zinc is uniformly distributed here. So because of that, you're getting hemispherical, but the iron is randomly distributed, in that you can getting a signal, non-uniform signal here. So you can able to identify that Fe cobalt, that position, the spectral position also in case of using the spectral mapping. And you have a core cell image, that you have a same different jet material like silica coated on copper sulfide or on zinc oxide. Because of the contrast between zinc and silica or Fe3O4 silica, you are able to see the core cell structure by mass thickness contrast. But you have a similar jet material, for example, a cobalt nickel. So both cobalt and nickel 27, 28 jet number, they are very close. So it's very difficult to identify that structure by mass contrast thickness. So then you have to go for a core cell STM imaging. You can see this is the STM image. Then on that, this is that spectral signal of that. This is of that of cobalt signal, and this is of that of nickel signal. Here the nickel and this cobalt and nickel, you can identify spectra, then merge here, you can get that how this nickel is distributed in the structure, and this is the alloying information that you can see. Initially you have a core cell structure, nickel and cobalt. The nickel is the center. You can see at the center mostly that green zone is coming here in the spectral mapping here, and then in the shell you have a red zone that you are able to see the cobalt structure because of the core cell spectral mapping. But when you go for sorry, this left image not cobalt nickel, this is PD and PT. So this is PD and this is PT actually, the not cobalt nickel. Right one is cobalt nickel. So here, so that cobalt is outside, you can see, and nickel is inside their core cell structure. And after that heating, it's a room temperature feature here. If you heat it at 800, 600 degrees centigrade, what is happening? You can see that red and green dot and mixing, you are getting mostly yellowish dot. So that is because of the core cell structure is changing towards nickel NiCO alloy. So because of the alloy structure, now the nickel cobalt is getting diffused to each other. So you are getting, instead of core structure, they're mixing each other, and you are getting a this type of spectral identification. So material having similar jet can be identified by electron mapping to get this structure. So another part of this electron microscope which you can use electron energy loss spectroscopy also by this TEM. So as I told that when electron is transmitted, it interact and it can, some electron beam can interact with the material, it's lost some of energy, that is inelastic interaction. So because of that, electron energy reduced after certain amount, that E electron will less than the E0, that incident electron E0 is the intensity energy, then E electron, the inelastic, the transmitted electron energy is less. In that case, the loss of energy is measured. You can measure that loss of energy by electron energy loss spectroscopy, and it has 3 regions, and there is, you can see here, this is the highly intensity one. In this case, is zero loss, that electron that have not lost energy, so totally elastic scattering here, so totally elastically transmitted, so it is zero loss peak here. And then there is low loss distribution and core loss distribution is possible here. So if you have a low loss distribution, electron that have interacted with weakly bound electron in the sample, those weakly bound electron that interact, so energy about less than 100 electron volt, that will give you, that low loss distribution here, this type of broad peak. So that will, because of low loss distribution of lower interaction, and the core loss region, you will get electron that have interacted with tightly bound electron cores. That the core of the electron, that at the center, the core electron, so they interact that there, that because of that interaction, so the energy starting from 100 electron volt and more in this region, you can see that you will able to get, that core loss information beyond this 100 electron volt, and in between there you can get a plasmon peak because of this electron interaction, and in the high energy loss, like in X-ray, that we get examples that near edge fine structure and extended fine structure. Here, LNS energy loss, near edge structure, and extended energy loss, XLAPS, it provide the information and get, like similar to XNS, you will get oxidation state from LNS spectroscopy, that energy loss, near edge structure, the near edge structure, this will give you the information of the oxidation state, but the extended energy, that is the oscillation you will get here. After the near edge transition, like in X-ray, you used to get, there is a near edge transition here, and then there is oscillation. So this near edge transition is here, that will give you the oxidation state, and this oscillation, but you get the extended energy loss, that will give information between coordination number and interatomic distance. So those information you will get mainly multi-electron structure, monthly interaction here, it is 1-1 interaction. So because of that, you will able to get all these, information from oxidation state. This coordination number can be possible by TM analysis by simply using yield spectra, and that yields can also use for elemental composition analysis, chemical bonding structure, energy filter. If you use, you can get this type of image. You can see here, this is this image of this bright field image here, and then that they define that yield mapping, yield EFTM. You can see that image you are getting, how the contrast is different, varying in this case. So you can also get from the yield spectra, you can have yields, you can create an image. You can see that from the backscatter, you can see it's not that good. You can see the clear features in case of this EFTM. And you can see the oxidation state. Here titanium is +4 oxidation state. Here titanium is +4 oxidation state. TiO2 calcium titanate. You can see the peaks here. In titanium is +3, depending on the binding energy loss. You can able to see here only 2 peaks. So then this is titanium +3. So that information +2, +3 by energy, from the energy loss, that particular binding energy, that energy loss corresponds to the particular element, and it's close related to the particular oxidation state, then you can able to get those information. And if you need, like EFTM, you combine with STEM with electron energy loss mapping, you can able to see this type of colored image, like where you have a titanium here, aluminum here, then you merge to get that spectral feature of that alloy or something by using this type of spectra. And now we'll go for, after this bright field, dark field, and STEM and Hill spectra, we'll see the high resolution TM microscope. In case of high resolution microscope, as I told, here both transmitted beam and diffracted beam both are used. That is phase contrast image you will get, or HRTM image you will get. You can see this is the incident electron, the sample surface electron beam is coming here. Then you have a both transmitted beam as well as diffracted. They, here some red and gray. You can see one is diffracted, one is transmitted. So both will interfere here, and you will get a phase contrast image. That means you are getting a big, aperture here. Objective aperture is quite big, so that you are taking the centered one, the direct beam, as well as the diffracted beam you are taking. So here you have to select a large objective aperture, and then image is formed interference of both. You can see this is the direct beam it's going, and this is the diffracted beam, this is the diffracted beam, and then you are getting an image here. So the interference of both direct and the diffracted beam both is coming, and you get a fringe contrast mode. Like you can see this type of the fringes image. So that you will be able to get. So mostly dark lattice plane, atomic plane, you can able to see how the lattice plane are arranged, how the atoms in that structure you can able to see, and by using depending on the operating condition, thickness and focus condition, and able to see that HRTM image. You can see this is an HRTM image. Here you can see all these lines are one plane. That this is, you can measure this image. You can measure the interplanar spacing here. That you can image. You can draw a line, and then you can see how this diffraction, this intensity across the interferences, this looks like here, and then you can measure this interplanar fringes. That is here is correspond to zinc oxide. That is about 0.26 nanometer. That is identified to the zinc oxide surface. And then you can see you have a 1 grain, 2 grain, 3 grain, and this is different grains in how that orientation is this direction, there is this direction, and this all the orientation you can able to find out. And then you can even see the atomic structure, how the atoms are arranged here. Those are each here zinc hexagonal arrangement of these atoms. That can be able to see at very high resolution image. So even you have a defect analysis can be possible by HRTM. This is grain 1, grain 2, and grain 3. When you have fusing of 2 grain here in this region, the 3 locations have identified. When 2 grains fuse, you can see that you can create an FFT image, Fourier transform image of the 3 location, and then you go for inverse Fourier transform. You can see here the lattice plane are clearly visible here, but in that you can see that the plane is coming here, and that one lattice plane, then it's diverting, it's breaking into 2. So here it is 1, and then it's breaking to 2. So this type of defect dislocation you can able to see. You can see clearly here this one diffraction beam here. This is going straight. This is going straight, but here this one is splitted here. So it is a dislocation. That dislocation structure you can able to see in high resolution TM microscope, and you can also able to see how the atomic arrangement, and if there are any defect structure, so the stacking faults in a material. It's a zinc oxide material where nickel is doped. You can see here these are atoms. Each atoms are seen here. You can see these dotted lines. You can see these atoms are arranged straight here, and then it should go like this line. But instead of that, you can see here the atoms here is slightly deviating its position arrangement. So that's this tilting is occurring, atomic plane tilting. So that is mainly due to stacking fault. If there is an oscillation inside the atom, the arrangement. So you can see the interplanar spacing is not same everywhere. That's because of stacking fault. So those type of fault information we are able to see. But if you have a biological sample, for that you have to go for a cryo-TM, and cryo-imaging is possible by using, so you can see at low temperature, like you have a liquid nitrogen or liquid methane, you have to, your sample has to prepare that liquid nitrogen, then you can able to see all this liposome image. You can see the unilamellar structure of each liposome here. That is clearly visible, and this is a micelle structure, so that micelles can be formed. So this is a biological sample you can see, or even this is a cryo-electron microscope virus. That virus can be seen. The advantage of cryo-electron, you can see the structure of the biology sample, because at high electron volt, if you use 200 kV, the biological sample will complete organic sample, they'll burn out, you're not able to see. But you can cryo-EM, you can preserve that structure, and you can that use mostly only 100 or 120 kV at low electron volt at huge, and this in a nitrogen environment, liquid nitrogen environment, you will able to see that all these biological samples. And you have many errors are there in the images, like you have a spherical aberration, like instead of meeting at a particular spot, they say they are deviating in a spread like this here. In case of focal point, it is shifted, like aperture diffraction, chromatic diffraction, you can see the focal point is different here, or astigmatism here. Some in the center, you have a diffraction point meeting here, and in the tangent plane is meeting other place. So because of this, the type of error will be aberration, that there are a diffraction error that will be interfere in your TM analysis. So this has to be, rectified before that analysis has to be performed. And then the important thing is here in case of TM is sample preparation. Like as compared to SEM, sample preparation at TM is much difficult. And like if you are preparing a sample, you have a very good sample preparation, you will be able to see the image in the TM. Otherwise, you will come out after a 3-hour analysis or something, you will end it with no or a very bad image. They may see a lot of aggregation, or you will see darker images. You will not able to identify the nanoparticles, or there is an yellowing or grain boundary structure. In case of metallic sample, you will not get. So sampling preparation, you have to take care properly. Like for example, for a bulk sample to preparing thin film, like for a metallic sample, you want to see a metallographic structure where, for example, carbonization or nitridization is happened, or some another intermediate phase is there. To identify that from bulk, you have to cutting a small piece, and then mechanical lapping to get a small piece, and then you have to do a ultrasonic cutting so that you will get a small thick. You will get a small slices here, like the slices you see 0.07 mm length, and then you have to dimpling, like you have to tilt cut here, tilting by dimpling, you have to go, middle layer you have to cut down, and what by mirror polishing or thing you have to do, and then by ion milling, what you will do, you will create a small transmitted hole like this, is very thin, this here, and where that electron beam can be transmit easily. So from the bigger sample to blocks smaller, the thin film, you have to create first 250 nanometer thickness space, then 3 mm discs, then 100 micrometer grind, and then 10 to 20 micro dimple that you create here. Then by ion milling, you can prepare this type of samples. So then if you want to see cross-section image, then you can see there is each layer is here substrate, different layer structure you want to see. Then you have to create this type of by glue, you have to join that, and then you have to cut at the using diamond saw section. You can cut that particular cross section, you will cut, and you will get this type of grid type, TM grid type things you will get. And then by ball milling, iron milling, you able to very low thick at the center, less than 10 micron, you can see. Then you can able to see that cross sectional information, and each layer information able to see by TM. But you have a nanoparticle or biological sample, in that case you have to use other technical way, like you have to disperse your sample in suitable solvent, preferably in ethanol or water. Water you can take if it's not less polar sample, but it's a more polar sample. Otherwise, you can take the ethanol or this methanol you can take, and then if it's not dispersed in ethanol, then you can use in a water medium. But if you use water, then sometimes to get vacuum, it will take more time, because vacuum in case of TM is 10 to the power -7 to -8 order. So you have to disperse in a suitable solvent, you have to choose, and by long-term ultrasonication 20-30 minutes, you have to prepare almost transparent solution. Your concentration of the particle has to be in such a way that it's not be translucent, looks like almost transparent. Then you drop carefully on the TM grid, just one drop or on the grid and one on the. But first you have to put your grid on a. You have to take a this Horstman filter paper. On that you put your grid, and first drop you put on the grid, and second drop you can put on the side, so that by diffusion it can go. So you don't put more than these 2 drops, then you can able to get good image. So for biological sample, you have to prepare, different staining way, that like you have to use a conventional sample preparation. Then you have to, since it's organic or biological sample, you have to stain it by with aldehyde fixation. Then you have to use a high jet material like osmium tetroxide, or uranyl acetate, or uranyl acetate, or tannic acid, or even the lead acetate. These are high jet material, organic component, so they may be burned. So for biological sample, you have to either use cryo TM. If you're using normal TM, then you have to go for negative staining. So that can be done by using the high jet material, osmium trioxide, tetroxide, or uranyl acetate. So that if your organic layer is like this, so this high jet material stick to that, and then you'll able to see that structure by negative contrast things. And then that negative staining for soft sample like myself facile you can able to do. And you can see here that this image, that you have a cell sample. That cell can be mounted on a fixed in a acrylic layer, and then that acrylic layer can be ultra slicing, and you can able to get a very thin cross-sectional thin TM grid like structure, and then that can be put on a TM grid, and then you can see on the microscope, you'll able to see inside that nucleus or the cytoplasm, all this, that how the nanoparticle are distributed, that can be seen. So other than that TM, there are other techniques which possible, they are available, like other microscopic techniques is used to get more similar or better information, like scanning probe microscopy. One is atomic force microscopy, AFM. There you use tapping mode or contact mode. So you have a sample surface, and you can put on a mica or silica surface, and then a cantilever that will scan on the surface what you'll able to see. Because of that, either by the force that depending upon the force that you can able to see the image. With the electrical forces that you will see EFM, electric force microscopy. By using magnetic material, you can able to use magnetic forces to MFM or magnetic force microscopy, or you can use a tunneling current that generate between this substrate or surface of the sample and that tip of your this cantilever. So you're able to keep the tunneling effect. Because of that, you can see the scanning tunneling microscope. So here you can get very resolution, good resolution microscope. You can get better images. You can all small structural nanolithography. All those things can be possible. It don't require vacuum, or it require very partial vacuum necessary. So like TM, SEM is this can easily, they can be prepared in a small space. It will require the instrumentation part, you see. And but the problem is that you have a scanning tip is there, so that tip is mostly damaged. If you do a tapping mode or contact mode, it's slightly higher speed, then it may damage. So the data may be affected. Detailed shape of the scanning tip. If you have a sharp tip, then you get an image. If you have a broad tip, that you will get, if you like this sharp tip, you'll get better image. So depending on the tip thickness, you'll able to see the spectral morphology, that microscopy images will be different. And then the slow occurring image with the tapping mode, like the tapping mode imaging is quite slow, and you can get an image size here in maximum image size. You have to small area of scan you will able to get. So these techniques I will not discuss because of time constraint, but you can go through all these techniques because sometimes you may use in your studies all those techniques. So in today's class, if you see the take home message, so we discuss mainly SEM and TM2 techniques we broadly discuss. In case of SEM, we use the backscatter electron as well as the secondary electron to get information about topography, morphology, composition, crystal structure information, as well as environmental SEM you can use for biological samples. But in the TM, you can able to see that shape, size, of the particles of there is an alloying or there is a coastal structure. Atomic resolution can be possible to get each atomic plane, and then that how the atoms are arranged. If the defect, those things you can get information, and you can using that yields electron energy loss spectroscopy, and you can able to find out oxidation state or bonding information, and you can by ELACS facility you can get that electron mapping, elemental mapping can be possible, whether it is nickel is there, cobalt is there, each element can be identified, and then you can get crystal structure information by electron diffraction pattern. You can analyze whether a crystalline structure, amorphous structure, or a single crystal, and by identifying the each plane, you can able to determine the particular crystal is formed or not. And I told defect analysis and interface structures, grain size and grain boundary analysis can be possible. For a biological sample, you can use cryo-TM, where you can preserve the structure of the biological sample at low temperature and see the morphology system like the liposome, the virus, those structure you can see. And if you can using the STM tomography facility, that you can able to see that if you have similar ZM material, like example I said platinum, palladium, or nickel, cobalt, that how this is the coastal structure is formed, and then how it's going to alloying those type of STM image you can get to see the coastal structure. So in an average, you can get quite a lot of information from both SCM and TM. But you have to take care about sampling step. In case of SCM, you can directly use the powder or drop cast on a brass top to get the information, and by gold coating or you can using that carbon coating, you can get the image, very clear, good image. But in case of TM, sample preparation is you have to prepare, you have to take proper care, like in thin film, like metallurgical sample, you have to analyze that ball milling and iron milling. By iron milling, you have to get the small thickness, then you can measure, you can see the micrography origin. Solution, you have to drop cast in proper way with proper concentration, so that you'll able to the concentration should be less, instead of aggregates and all these things. We'll see nanoparticles are distributed throughout the grids. So the next class we will discuss that is the last class from characterization part, where we will discuss that X-ray photoelectron spectroscopy and Auger electron spectroscopy, as well as secondary ion mass spectroscopy, mainly the surface characterization, that we will discuss in next class. So if any questions, we can discuss right to here, otherwise you can mail to me. So you can type in chat box if there is any questions. Okay, since there is no question, so we can conclude today's lecture here. So we'll meet on next Tuesday for the last class on X-ray photoelectron spectroscopy and Auger electron spectroscopy, as well as secondary ion mass spectroscopy.